So hi everyone, and welcome to the AI Hardware Show, after show, podcast, general chat. This is for episode 10 of our series. If you haven't seen episode 10, there will be a link in the description below. My name's Ian Cutress with More Than More, and joining me, as always, Sally Ward-Foxton from EU Times. Now, this episode is a little bit of a mix of training and inference and
neuromorphic, other cool stuff.
Yeah, this is the thing with the AI hardware space. There are so many people trying so many different things.
It's all about variety, but there are a lot of niches as well that people can go into. So we do need different types of hardware.
We may have an American audience. You have to say niche.
And I will refuse to say niche. It's niche. It's always niche.
Or it's patent, not patent.
Oh dear.
So we started this episode speaking about Synsense. If you've not heard of Synsense, it's because they're a startup.
It's because they're a startup. They're one of several, I was going to say many, but certainly several startups out of ETH-Zurich, University in Zurich.
Yep.
So they're one of these really fun neuromorphic processors that I think we've spoken a lot about spiking before, and this is definitely a spiking processor. But they kind of simplified their model of the neuron a little bit. Not a lot, but a little bit.
Neuromorphic digital, lots of companies say it's inspired by the brain, which has neurons and synapses. So it's all about where a spike occurs in the brain and then how it propagates through the network, and that's your compute. But we're seeing companies do it entirely in digital format.
Absolutely.
So normally you'd think of that as an analog process, but digital. Not only Synsense, but Luihi and Luihi 2 from Intel.
And BrainChip.
And BrainChip, and I'm not entirely sure what Spinnaker does, but I think that's digital as well.
So I think, there are arguments for and against analog and digital, but I think digital is definitely more mature at this point for spiking processors. So
it's also very easy to propagate. To just put loads of neurons on chip, and we're actually finding that a load of these chips have custom onboard networks because the network has to be arranged differently.
Yeah.
When you're recording time-sensitive data, even if that's simply a list of when spikes occur, you need the architecture to do that.
Yeah. You need to also have a good handle on, how spiking networks work, which is also still very much an emerging technology. We're talking about it as if it's a done deal here, but it really isn't. One of the big things with spiking networks is how do you train them? Still an open question.
Yep.
Synsense has its own version of that, which is approximating the derivative of the spike. So you can do backpropagation on a spiking network, which normally I would say isn't really possible. So they say it gives you better accuracy than the BrainChip version, which is more like a conversion.
So we've covered BrainChip in a previous episode. They train a network traditionally and then convert it
into the spiking domain. But there is a third way called STDP, which is a training method specifically for spiking networks. But BrainChip does a bit of that for the one-shot learning at the edge. But Synsense doesn't. I don't think they use that one. They use backpropagation for training the networks.
We speak about machine learning as training, then inference. Training the big models, inference is on the really small chips. Lower power, less compute to do, but in our brain we kind of inference and train at the same time
on the same hardware.
Or with the same data. It almost as if it's the same mathematical process, right? No matter if you're doing an inference, it counts as a training instance.
Right.
Whereas in chips, in silicon, in software, that's hard to do.
Yeah.
And I think some of these companies are saying, well, we're having a solution, say with the spiking neural networks, that might be able to do that in a certain way.
Learn as we go along a little bit more, supposedly more like a person. It's easy to imagine that in a robot that kind of learns exactly kind of what it's doing as it goes along.
Whereas right now, that model, in society today is let's just collect inference data and select some of those inferences to train on, like the self-driving. It just records data, which then goes into later training. It doesn't train while it infers because that requires today very different hardware.
Yeah.
So, and with asynchronous digital spiking, which is a word for whichever way you put it, you do it. You've got companies who are A, trying to emulate the brain because that's fun, or B, actually trying to put it towards useful work, even if it doesn't. So we're getting this mix. So for Intel's Louis 2 is more of a research chip than a productization chip, just to actually get those sort of neuromorphic spiking networks on the road. Whereas Synsense and Brain Chip, because they are startups, they have to get customers. So they have to be a lot more practical on this.
Yeah. So Synsense already has partnered with Prophecy and Innovation on the event-based cameras.
Right.
I'm thinking there's a synergy between, the very low bandwidth signals you get from the event-based camera, which is also kind of brain-inspired or retina-inspired, and then combine it with the neuromorphic processor. So, so like ultra low power, super fast latency could be really cool.
The demo these companies like to put out is we can detect smells.
Yeah, that's another thing, because it's brain-inspired. It's like we want to do all the different senses. So Brain Chip has one that tastes wine, for example.
I can taste
but
wine.
Smell detection on Louis as well.
Yeah, because for a smell in your nose, you have receptors, and when a molecule hits a receptor, it generates a current, which is an event, and so it's event-based processing. And the idea is that with these neuromorphic brain-inspired chips, you have events, and part of the difficulty with that is actually creating the sensor.
Yes.
To do that, because a video camera isn't an event-based device. It's ton of data all the time.
Yeah.
You need a neural network on the camera to detect a person, and when you see a person, that's an event.
Yes.
So that's the way you kind of have to think about these sorts of sensors.
Yeah, they're kind of looking for differences between the frames, basically things that are moving, lighting conditions that are changing. Or if you're an autonomous vehicle, everything around you is moving, but you're just detecting the edges of all the surfaces and so on. So it basically means, you just get white dots on a black background, ultra low bandwidth, and you can do it. Then you can process it very, very quickly, which is important.
So also in this episode, we covered Intel's Keem Bay, which is a code name, and Intel likes its bays, it likes its lakes, it likes its rivers. And the reason why companies choose location names for code names is because they're non-copyrightable, and legal doesn't get involved. So that's why. So Keem Bay from Intel comes out from the Movidius acquisition. So this is years and years ago now, before Intel acquired Nirvana and Habana, and Movidius was all about small video processing units. Now, if you know the history of machine learning and AI, all this stuff was essentially kind of theorized in the 70s and 80s, and a lot of research was done into at least the entry-level mathematics into it. But nobody had the compute power to do it, or the right way to do it. So for things like video camera detection, because one of the industries that is actually leading in video camera detection at the time was casinos. Because they need to identify people, so the point is, if you're found cheating in Vegas, you're
banned.
You're banned.
Get out.
You can't fly to Macau the same day and go into another casino, because you'll be banned from there as well, because the camera will detect you. So this is vision processing, vision compute, and that's been about for decades. But it's not AI based; it's very semantic in the code.
Yeah.
And Movidius came about at a time when that was still the major play.
Yeah.
So their first generation and second generation parts were all focused on accelerating that type of workload. Small M.2 chip, power form factor type stuff.
Yeah. In a drone flying around, looking where it's going, that kind of
Yeah, because Intel used to be all about the drones as well.
They love drones, yeah.
Well, they loved.
They did.
It's been cut since, thank God. So now this third generation Keem Bay introduces more of the traditional AI compute for video. And this chip, I said in the episode, it's been about since early 2021 for customers, but wasn't really showcased until last year to the rest of us. And I was at Intel Israel. They had Nook, one of Intel's next unit of computing, small PCs with an M.2 card in with one of these processors. And the demo they showed is OBS, which is video streaming software. Anybody doing a live stream, this is one of the software options you use. And of course, in a live stream, if you're on Twitch, there are people who want to put AI overlays or bottom banners or special effects, or even something as simple as like a blurred background. You can either do that using semantics or with artificial intelligence for that. And they were showing lots of use cases for this VPU. in OBS,
Yeah.
which I thought was a great way to offload that from the CPU or the GPU. Also, optimizing the audio, cleaning the audio up. And also in Task Manager, it listed VPU 0. So you could have VPU 1, VPU 2, just like you would have multiple GPUs.
I see, yeah.
And it kind of makes sense. The downside of all this is Intel's not selling that as an M.2.
Oh.
What they're going to do is integrate it into future generation mobile processors, as in either on silicon, basically, in package.
Oh, right, okay.
Either as a separate tile or in like the CPU or the I/O silicon, which is good because then it becomes ubiquitous among all.
Sure.
But bad because I really want it in M.2 format. The whole point about offloading from the CPU and GPU is that it's in a different chip that has a different power budget.
Yeah.
Right. So I kind of mentioned in the episode the reason why I think, depending, I may have edited it out. The reason why I think they're doing that is because they don't want their M.2 device being used in non-Intel CPU environments, which is...
It's like they're cutting off their nose to spite their face a little bit.
The CEO, Pat Gelsinger, speaks about being a lot more open and a lot more integrated with the rest of the industry. And if you offered that as an M.2 card, people would buy it, install it in the systems, using the OpenVINO toolkit, and maybe it might become part of the One API stuff, and then people write code and plugins for it. Whereas, we had a situation, Intel had AVX 512 on its consumer processors, and that was ubiquitous, but again, very limited use cases for it. This, I think, has potential, but they have to realize that. I don't know.
If you're watching, Pat.
Pat's not watching. Other Pats will be, though. But I mean, the amount of meetings during the pandemic we had remote, and we're still having, or conferences or whatever, having that sort of you can tell when somebody has a bad background replacement algorithm because it's blocky, it's choppy.
They're better than they were at the start of the pandemic, though.
Yeah.
Yeah, they're better than they were.
I mean, I've even published interviews with people that had the fake background on, and then every so often you'd see the dog come in and out. And so I had to decide what to do with that in post-production. But
keep the dog always, no?
So, or child or husband.
Yeah.
Yeah, that sort of thing. So it's, I've had this argument with Gordon from PC World. What uses for AI and machine learning are there in a consumer system? And
count the ways.
Well, but in a smartphone, it's obvious that most of them are in camera.
Yeah, your Instagram filters and
in a laptop. Okay, the camera for meetings, but you don't use that to take photos.
No, but you have smaller AI chips doing stuff like, are you actually looking at the screen? If not, we'll lock the screen. That kind of thing. So, or security maybe. Fraud detection, that kind of thing. So these use cases have to develop, and I don't think there's not going to be a killer one. And Keem Bay is the example of now we're finally putting them into CPUs as dedicated accelerators. We've had video codec accelerators for years. Now let's have AI accelerators like the mobile space. Yeah. But software has to exist. So going from the super, super, super tiny to something a bit more chunky. Yeah, this one's a beast, and they've called it Thor, obviously. So they scrapped the design they did have for kind of centralized controller for the car. This is NVIDIA. They had one called Atlan that they were going to do, and they totally scrapped it, and they've replaced it with Thor, and it's like even bigger. 2 petaflops, absolutely massive GPU. So this is a Hopper generation GPU.
Right.
Which is great because you've got the Transformer engine, you've got other cool Hopper-like features, but you also have, which was actually introduced with the Ampere generation, MIG.
MIG.
Have we talked about MIG before? Do you want to talk about MIG?
MIG.
MIG is cool. Multi-instance GPU. So basically have a really, really big GPU and you split it up into 7 small GPUs.
Virtualization by another name.
Yeah, basically.
Do you have to pay a license for?
So I think this is the first time, to my knowledge, I think you probably could do it. This is the first time they're actually promoting it for doing graphics workloads as well as doing AI workloads on the same chip, which you need in the car if you're doing absolutely everything in one centralized domain controller. You have your instrument cluster graphics and so on. You have your infotainment, you have all that cool stuff in the car, but then you also have the AI that you need for autonomous features as well, all on one chip.
You also need that, securely separated from each other.
You need the instrument cluster to work. Who cares what the infotainment is doing?
Yeah, so
let's not crash.
If the infotainment crashes, you still want the self-driving.
Exactly. So it's good to have isolation between those. Yeah. And NVIDIA, obviously, they thought of that.
Yeah, I mean, MIG, when it was initially introduced, it was for some arbitrary reason it was 7 per GPU.
So it's got to be 8, and they use the 8th one for something else, right? There's no way there's 7s. There's no way it splits into 7. Nothing's divisible by 7 in computing. It's always 8.
Unless you count 0.
Well.
But then it's still 8.
But then you'd still get 8. You'd still get 8.
So, and because something like this was kind of possible in the past, but there were limitations based on licensing and exact, and I think it wasn't 100% secure either.
Yeah, security is new for the...
Yeah, and I mean, we often think about NVIDIA in the sense of big data center scale environments where you have one user to multiple GPUs, and now you have multiple users, different parts of the car per GPU, and that's got to pass all the ASIL tests and
absolutely
ADAS.
Absolutely, it's a whole different ball game.
And then it gets installed into cars 5 years in the future.
So they say 2025, which is.
Did they mention partners?
Yes, there's an autonomous driving company beginning with Z. They've already said that.
Oh, is this Zeekr? Zeekr in China.
Yeah.
Which are also doing Mobileye.
First customer for it. So.
Yeah, I mean, autonomous driving. Everybody gets excited when it's personal. But to be honest, the bit where it counts most initially is going to be the big long haul truck.
Oh, yeah.
Supply.
Yeah.
So, I mean, it'd be nice to get updates on that side of thing as well, because you're less power limited. Everything can go above on the cab, and yeah.
Yeah, I don't know. I want an autonomous car. So, I don't want to have to drive. I really want this to work. So
I'm not sure if I mentioned this before, but I ran, and I'll cut it if I did. That'd be a big. You mentioned this before. I ran a poll a couple of years ago on my Twitter. How much would you pay above the base cost of your car for full autonomous driving? And the options were 10% or less, 10 to 20%, 20 to 30%, or 30% to 50% plus.
Yeah, 20 to 30%?
I think I'd pay 50%.
You'd pay 50% more?
I think, because it frees up so much of your time, if it can do everything.
If it really honestly can do absolutely everything, and I can sleep, then maybe it is worth it.
Yeah, whereas level 4 plus to level 5 is that last little bit of...
It's quite a big jump, yeah.
Do you still need a steering wheel? Level 5 you don't. Level 4 plus you do.
Yeah.
So
I mean, if I'm paying 50% more, I want to be able to trust it as well, and I think that's where I'm going to struggle.
Yeah, I mean, there's this argument that the technology will be there, the legal system won't.
No.
So I don't know. And then so later in this episode, so a lot of what we've spoken about in this series has been chips, because you can't speak about AI hardware unless you're speaking about actual silicon. Though there are companies in this industry that don't produce silicon, they just create the designs, the blueprints. These are IP companies.
Like ARM.
Big one is ARM. And then you've also got companies like Sci5 on the RISC-V side.
You got Siva. You've got a lot of little AI companies now only doing IP. I mean, there's tons.
And so the one we spoke about in this episode is called Quadric, not Quartic.
No, definitely Quadric.
And for some reason, I keep wanting to write Quartic. It's like inference and integer and integration. But so Quadric is an IP company that are trying to simplify the machine learning process. So modern machine learning workloads, you've got your compute, but on top of that, you may have control where you need to move data around between compute cores to make sure everything's set up right for the next essentially cycle. Mm-hmm. And then you've got So you've got memory control, you've got network control, you've actually got compute control. And you may have matrix engines, you may have vector engines, you may have scalar engines. Quadric's solution is we're going to do all of that for you.
Yeah.
We've got IP that combines all these engines and all these control points, and we're going to bundle it up in some IP and have this software stack that you can integrate it. And the idea is that if you compile it to a framework that we support, we'll just make sure it's as efficient as possible on our hardware. Trust us. And unfortunately, I think that's the bit which may not get a lot of traction. So we speak to companies and they're like, yeah, we support Onyx, TensorFlow, Caffe, maybe Paddle, PyTorch. And the whole point is you create your model in that. You use their compiler and then it runs. That's kind of what Quadric is saying. But some companies are now saying, well, we need a lower level language for the people who want to really optimize it. Because even if you compile, say, your PyTorch model to their hardware, you may only get 50, 60, 70% utilization at best. And then how do you do more tuning on that? You kind of have to get around the deficiencies in the compiler and PyTorch in order to improve that performance, unless you have access to a lower level language. And what Quadric is saying is basically we've not only do we have the compiler, we have the optimization engine that makes it a lot simpler for your code at the PyTorch stage, which sounds interesting. And we all know that machine learning or FPGA use, for example, part of the difficulty is you don't want people to learn about the hardware. You just want them to be able to code.
Exactly, yes.
And train and stuff. So simplifying that makes it a very easy way to get in. Though given how quote unquote easy NVIDIA stuff is, I'm not sure another, especially an AI IP startup, can compete with that.
Yeah, I think everybody's going up against CUDA.
Yeah.
Everybody is going up against CUDA, and it's quite a tall order. CUDA's been around for so long. Mm-hmm. And thousands and thousands of people working on it all the time, improving it all the time. I think it's going to be a tough nut to crack.
When you've got 10 years more than of embedded academic research, and then those people now are the leaders in AI compute on GPUs, any company coming into, even Intel has problems, AMD has problems, because you need to start investing money in the ground roots.
Absolutely.
If there's anything that's going to dislodge NVIDIA from that space, it is machine learning libraries being available that just compile to target. And to be honest, I kind of think that's kind of what Quadric is trying to do here. That's what Intel's One API is trying to do, for example.
I think One API is quite a good idea. It's quite fun because it means you can change hardware with the same code.
You still need to compile.
Yeah,
to target.
But you don't have to start again.
Yeah.
So I really like the idea behind that.
Yeah, the feasibility of it.
Yeah, does it work? And it doesn't work for Habana, or not yet.
Not yet.
So yeah, it's still a work in progress.
But I mean, we'll see. It's IP-only companies have the deficit of not having hardware. And a lot of companies we've spoken about have taped out a chip and can speak about tops per watt, process node.
Yep.
With Quadric, if you're an IP company, you don't have to do the post-chip validation, which may throw up some additional errors in your design that you need to optimize out or anything else. And
it also means there's more flexibility. If I'm the customer, then I can tailor it. Maybe I can scale it up or down, and then I can pick the process node that works for me, my cost and performance point.
The danger with startups is if you do that, then maybe the optimizations you do for that customer don't apply to anyone else, and you could have spent that time offering optimizing for general features. It's a double-edged sword.
It is a bit of a double-edged sword. I think they'll be going for first customer. Got to be customer focused at least at the beginning.
Yeah, for sure.
Have they announced any customers?
Not that I can remember.
Okay. They were another one that was initially going with automotive, and one of their big investors is Denso, the Japanese tier one.
Right, okay.
So they had kind of automotive, I think, in mind, or partly in mind from the start. So it could be that Denso is making an SoC with this on, and we're speculating, but it could be.
Denso's also, I guess, the type of company that doesn't talk about what IP they're using.
Yeah, no, we wouldn't know in that case. We wouldn't know.
But speaking of IP, one company that's heavily leveraging IP from other providers is Esperanto.
So it's a big RISC-V.
Yes.
RISC-V design with 1,000 cores or 1,000 and some cores. It's not the only 1,000-core RISC-V design now. It was when it launched initially. But yeah, despite being 1,000 cores, it's like 20 watts or something. So it's, going onto these little cards that go onto the big Glacier Point, kind of bigger cards for acceleration in the data center. But yeah, it's specifically for recommendation, this one, which is interesting. Interesting workload. I think we've spoken about recommendation before, so...
Yeah. But the brief up and down of it is recommendation, your Amazon, your Baidu, everybody else, or even, say, Google, YouTube. You've got to... If you're more accurate, you can get people to spend money, but you also need to be quick.
Yes, it needs to be accurate and fast. And the nature of the workload is such that it's difficult to accelerate with GPUs and other kind of more like AI accelerators because it's slightly...
You need different types of memory on board next to the compute in order to accelerate because...
You have these huge embedding tables that need to be in memory and so on. So it's a little bit different, shall we say. So it's a tricky one.
If you've got 250,000 products and each one has a weight of this customer is most likely to buy this, it then becomes a super sparse matrix multiply and you have to be able to do that. What I like about the Esperanto design is when they were doing public disclosures of the chip, they were talking about performance per watt and how their chip can scale from down to 2 watts and go all the way up to 70, 80 or more watts. Now, because they wanted to fit this, what they call OCP, Open Compute card, Glacier Point card, you're limited in terms of your thermals and your density. So they found that actually 20 watts per chip and 6 chips in that form factor was the point at which you not only got the peak performance for the power, but on top of that, the peak efficiency for that design.
Yeah, and as much kind of I/O with memory as you want, because you want tons of memory for this as well. So it was the multiple small chips was better than just doing one big massive
chip,
one,
or one chip at really high power.
Exactly.
Yeah. Which makes sense. And
exactly.
I don't see many other companies doing that for that solution. They're either doing the one big chip or multiple big chips with the power budget just wherever it is.
So they have cool low power features as well. They design their own SRAM to run it at lower voltage to try and save a bit more power. And I think there's some cool features to this chip, but the use case is quite fixed and quite specific.
Yeah.
There's half a dozen customers or something, potential customers, in the world. But if you can get into one of those, then
you improve your recommendation accuracy by 1%. That's millions of dollars.
Yeah, then it's worth having, right?
Yeah. So, and then the last chip this episode from Intel, their big training Gaudi 2. So this is from the Habana acquisition. Habana has its own architecture that's different to Intel's general architectures, and so we've covered Intel Habana chips on the show before. We've done Greco, which is their small inference design, Gaudi and Gaudi 2 now, big training chip, right? And it's optimized a little bit for video processing. One of the biggest customers here is Mobileye, again, another Intel subsidiary, and they're self-driving, so you need video processing. It's got video encode and decode engines on board to help with that. And the whole point here is having a chip that does a lot of matrix multiplies, but it's optimized for utilization. Mm-hmm. So the argument here with Gaudi 2, 96 gigs of HBM2E memory, is that with a 1K by 1K matrix, you can get 100% utilization. You try and do that on a GPU, it ends up splitting it up into separate smaller parts, and in order to get even 80% utilization, you need a 3K by 3K or a 9 times bigger matrix. So this is very much a training focused. If your matrix engines are that big, it doesn't work out well for training because your matrices are very often several times smaller. And the point of having such a large matrix multiply engine is if you're bigger than that, it works. If you're smaller than that, you're not as efficient.
Yeah.
So very training focused. They're actually already deployed in Amazon instances.
Yep.
So if any of you wanted to get access to them in the cloud, they should be available now, or at least on a list where you can put down your email to get access. And I think what's somewhat frustrating with this, and what's going to be frustrating for a lot of these AI companies that aren't NVIDIA or Intel CPUs, is how do you get access to them in the cloud?
Yeah.
You need a hyperscaler to support them in sufficient volume. And when a hyperscaler has 100+ options to choose from, who do they go for?
Yeah.
We're seeing some of these companies are actually looking towards the tier 2 hyperscalers and deploying there.
Yes. Yeah.
So I know, for example, Cerebras is in a couple of smaller hyperscalers, and now they're offering their own cloud instance.
GraphCore.
Yeah.
That's Graph Cloud.
Graph Cloud. And, IBM has some of their IBM Cloud stuff as well. And we're at this point where if you want large adoption of your hardware, it needs to be available. Because otherwise it then becomes you have to phone up the company, express interest, then they'll discuss working with you, and then you have to find the right point to start working with each other. Now, I find that a lot of people who want to implement machine learning in their product stack, whatever, they just want to try several different options without that interaction. And you can do that in the cloud.
Yes, absolutely.
Or you can do that if you buy. If you
Yes.
can actually go to Newegg or a distributor and say, I want a Supermicro system with 8 cards or 1 card, or you can simulate it, virtualize it. The problem here is that we know one big customer with Gaudi 2. You can say Amazon's the second, but they're more sort of an intermediate layer, right? So if Intel wants to push this hard, then they need to start talking about more and more customers using this hardware.
Yeah.
Even if it is new.
Absolutely. Absolutely.
I did see a big, when I was at Intel Israel in September, I saw one of these big 8 Gaudi 2 systems. I think what fascinated me more was the fact that it was powered by 6 4-kilowatt power supplies.
Wow.
If you've ever seen a 4-kilowatt power supply, about that long, and you can guess how loud it is. When I started pulling out the power supply from the back of the Surfer, they were like, what are you doing? And it wasn't turned on. Let's just be clear. It's like, no, we want you to talk about the chip, but this solution is important.
Yeah, okay.
So, yeah, it's an uphill battle. And to your point earlier about one API support, these chips need to be integrated into.
They absolutely do, yeah.
In order to pick up traction, essentially, and be able to emulate for them, get access to them.
Yeah, I mean, it's about perception as well. Being able to say, oh, it's here, it's there. It's, you can get access here and there. It's about kind of perception as much as having people actually try it. So
we'll see.
Yeah, we'll see. We'll see what happens.
We'll see. So thanks, everyone, for watching this after show podcast, videocast, whatever you want to call it, about this set of hardware. We've got another few coming up. So stay tuned for those. Thank you, Sally, as always.
Thank you very much.
We'll see you in the next one.